Alright, so in this video, I'm going to do a recap of today's lesson on orbital hybridization. So I'm going to do my best to break this down so that it is in manageable pieces and to hopefully explain at each step along the way what is happening and why it's happening. So I'm going to start with carbon. And so you should have a periodic table handy while you're listening to this video so that you can make sense of some of what I'm going to be discussing. So if one were to look at the periodic table, you would see that the valence electron configuration or orbital diagram for carbon would be written as so. So there would be 2 electrons in the 2s orbital and then 2 electrons in the 2p orbital. But if we're talking about carbon making 4 bonds, which we know it does quite often, so for the purpose of bonding with 4 ligands, we know that there needs to be 4 bonding electrons, right? 4 unpaired electrons in order for bonding to happen. And right now we only see carbon having 2 electrons that are unpaired, and so the most it could make would be 2 bonds. So one idea that was proposed in class today was that, well, what if one of these 2s electrons was moved into the 2p? So let's take a look at that. So that would give us the following orbital diagram. And so that is definitely better. We can see now that we have 4 unpaired electrons around our carbon atom. So if in, say for instance, a molecule like CH4 methane, we would have carbon with 4 available spots in order to bond. So we are getting there, but there's a little bit more to the story here, the things that we need to consider. So let me draw a little picture of what this would look like. So again, we're going to pretend here that we're looking at the molecule CH4 methane, CH4. So we need to remember also that along with that, we would have 4 hydrogens. So right here, what I have is just carbon. And so I also need to think about, well, what would the electron configuration be for our hydrogens? So let me put that in here. So each of our hydrogens has 1 electron, and so its electron would be in the 1s orbital. So I'm going to draw 4 of them. And I'm running out of space, so I'm going to do my best here. Right. So there are my 4 electrons from each of the hydrogens, and I have 1 carbon, and here's my carbon right over here. Right. So let's start with carbon over here. I'm just going to draw a little picture of what this would look like, so that you can visualize. So if I have carbon, I can see that carbon has 3 electrons each in p orbitals. So it may be helpful to think of this as px, py, and then pz. And so I can think of it as, the px orbital maybe looks something like that, so like that, right? And then maybe and here's a hydrogen on the px. So then I've used up that electron, I've used up one of my hydrogens. There's a hydrogen. Going back, I'm going to do maybe like a py here, orbital. And now I'm going to do that on that py, I'm going to draw a hydrogen. So there's my ps overlap. So there's my py electron used. Now I'm going to go over and I'm going to draw a pz orbital. So I'm going to try to draw that sort of coming out of the board. Boom, like that. And then here is my hydrogen in its s orbital. So there are these 2 orbitals overlapping that I can get rid of in the mix. So what is left here? Well, I have 1 of my carbon electrons in an s orbital, and then my final hydrogen is in an s orbital. So to show that, what I would need to have, and I'm going to do my carbon s orbital in yellow here, it would be here, and then I've got my hydrogen on it overlapping here. Well, if I look at my bond lengths, it appears as though I have 1, 2, 3 really long bonds, and then this one little short bond formed by my SS overlap. Now, that can't be. And why can't that be? Because we don't observe this to happen. This is not what methane looks like. Methane is a molecule with 4 equal bond lengths. So clearly, there's a problem still with how we have sort of positioned each of these electrons within the orbitals. So here comes in the idea of hybridization. So that would create a molecule, like I said, with 1 short bond and 3 longer bonds. So 3 sp overlaps, right? sp, sp, and then sp or overlaps, and then this ss orbital overlap, which, maybe this last, let me see if I can move this little, no, I can't do it. Maybe this green orbital should be on the other side, but whatever. So we know that that can't happen. It's not how it works. So here comes the idea of orbital hybridization. Well, let's talk about what a hybrid is in general. So a hybrid is really just a mix, right? Hybrid, so think like hybrid vehicle is, a vehicle that runs on both gas and electric fuel, right? We can think of a hybrid organism like a mule, which is a combination or a mix of a donkey and a horse. So a hybrid orbital just involves mixing orbitals together. Let's take a look at that. All right, so to explain the observation that methane has those 4 equal bond lengths, they had to come up with an idea that best explained what they were observing. So if we were to look at the electrons as we've just seen them for carbon's valence orbitals, we see that we have 1 electron in the s orbital and then a total of 3 electrons in the p subshell, px, py, pz orbitals. And so the idea of hybridization would involve taking all of those orbitals and sort of imagine like a big mixing bowl of orbitals, mixing them all together. And, no matter how many orbitals, whatever number of orbitals that go in have to come out. So I want you to envision that we're taking a big mixing bowl of orbitals and we're combining them, but that each individual new orbital, so I'm going to have 1, 2, 3 orbitals, so 4 orbitals, is going to be 1 part s and 3 parts p. 1 part s, 3 parts p, and so on and so forth. So by doing that, we have 4 orbitals, each 1 part s and 3 parts p. But the important thing here is that each of these orbitals is identical and will create 4 bond lengths that are of equal length. That's the idea. So you might be wondering, well, I know what an s orbital looks like. I know what a p orbital looks like, whether it be the px, py, pz. But what the heck does an sp3 orbital look like? Well, as you would expect, it's 3 parts p and 1 part s. So it's going to have some strong p character there. We can see a bit of the s. So now we say that, and we know in methane, if I were just to ask you, well, what does a molecule of methane look like? What would Vesper predict its, electron arrangement would be? What would it be its molecular geometry? Well, we know that it would have that sort of traditional tetrahedral shape, right? With, kind of like this. I'm not going to fill that in. And there we go, right? So it would have that tetrahedral shape. But, so how does that work with these sp3 orbitals? Well, let me see if I can pull this off here. So I'm going to try to trace. Let me see. I'm going to try to trace here. I can already see this is kind of failing, but let me see. If I were to take each of these 4 hybrid orbitals that are of equal size, now let me see if I can move these around. Nope, it's not going to let me do it, folks. I want you to imagine that if I took all of these orbitals and overlapped them, they would indeed form a tetrahedron. But you'll just have to take my word for that. All right, moving on. Okay, so let's see how this works out when we're talking about molecules and overlapping orbitals in molecules. So I'm going to arbitrarily call this carbon right here carbon 1 and this second one carbon 2. And I'm going to look at their, what I would expect for their atomic orbitals, how they would be sort of lined up. But then I'm going to remember that I need 4 equal bond lengths around each carbon. And so I'm going to see some hybridization happen here. So, right here, all of those 4 electrons would form 4 sp3, so 4 times sp3. And the same would be true down here, 4 times sp3 hybrid orbitals. So you will remember that in a sigma bond, any single bond is going to be a sigma bond, but then we have direct overlap. So what I'm going to see around each carbon in this molecule that I've drawn is an sp3 orbital, sp3, sp3, and sp3, right? 4 orbitals around carbon, each of equal size or shape. I know hydrogen only has 1 electron, and so that has to be in the s orbital. So every hydrogen in this diagram is going to be an s orbital, in an s orbital. But the carbon-carbon bond here is going to have to be an sp3 overlap. Sigma bond. So there we go. And if we really think about it, the molecular geometry about this carbon here is in fact tetrahedral, right? I have 4 ligands and no lone pairs. So there we have it. Okay, let's move on to the next section. So here I have this visual for you of this. So here we have 2 separate carbons, each with 1, 2, 3, 4 sp3 electrons or orbitals with a single unpaired electron in them. Right, here we go, carbon number 1, carbon number 2. Right, when their atomic orbitals overlap, their sp3 atomic orbitals overlap, they form a sigma bond, and so now we have a molecular orbital, right? So it's not drawn in here, but if we were talking about a molecule of ethane, we would see all of the hydrogens with their s orbitals carrying an electron, right? So I haven't drawn them perfectly there, but I would have the electron of opposite spin filling that orbital and complementing carbon's sp3 electron. All right, moving on to, I'm going to use a molecule of ethene or ethylene to discuss carbon-carbon double bonds and how orbitals will hybridize in this circumstance. So you will remember in yesterday's lesson that in any double bond, you will always have one of the bonds is going to be a sigma bond and the other is going to be a pi bond, right? So I'm just going to indicate that right on my diagram. Let me zoom in here for just a little bit. And so I know then, therefore, that if you can remember that a pi bond, I'm just going to draw a little picture here sort of on the side. A pi bond is going to have orbitals that are sort of at a distance, and there's not really a direct overlap, which is why a pi bond is a little bit weaker. So pi bonds will form in carbon as a result of p orbitals overlapping sort of at a distance, right? So I'm going to put in my electrons for each of these carbons. So if in fact I do have a pi bond, that forms as a result of an overlap of the p orbital electron of one of my carbons and a p orbital electron from my other carbon. So here we go. So those are actually sort of out of commission. Let me do that in a different color. Out of commission, out of the mix. And so I'm going to just write in that this is a p overlap happening here. And so now, let's take a look at, well, what's left over. Well, what's left over for each carbon are 3 other electrons available for bonding. And I see on carbon I have 1, 2, 3 other lone electrons that are in a bonded pair. So what's going on? What kind of orbital are we forming here? Orbitals. So there we go. I have 3 leftover electrons that have to be hybridized to have equal bond lengths. And so what results is, well, what I have left is 1 s and 2 p's. The resulting hybrid orbitals that form are sp2 hybrid orbitals. So I can indicate that on my carbon. Here's an sp2 orbital, sp2 orbital, and sp2 orbital, 2, all around my carbon. And of course we would see that mirrored in the other carbon as well, because the same situation would arise. Right? Let me go back for a second here. I would see that carbon number 2's electrons would do the same thing. I would have instead 1, 2, 3 orbitals, but each being 1 part s and 2 parts p. Remember, the total number of orbitals that go into the mix have to equal the total number of orbitals coming out of the mix. So I can go back and just indicate that. sp2, sp2, sp2. Okay? And of course, we'll remember that all of the bonds around, all of the orbitals around hydrogen are s orbitals, as we saw before. So let's try to visualize this, right? So we've got 2 parts here. We've got the pi bonds going on, formed by the overlap of our p orbitals, but then we also have, and so that's what you can see here, here are just the p orbitals of each carbon overlapping at a distance, right? There's our pi bond right here. But we also have, and here's the second picture, we also have our s orbitals overlapping, right? So, we also have our sigma bonds happening here. So, here we go. So we can see the direct overlap here of our sp2 orbital, so sp2, sp2 overlapping, right, and complementing each other, forming an sp2 molecular orbital. Then we also see here are other sp2s. So here we have our sp2 hydrogen s orbital overlapping. Now let's put this all together. So if we put, and this seems daunting, but I promise you, let's just take a look at it and it will be fine. So showing the 2 carbon atoms separately and their respective orbitals, we see, here's our p orbital, which are overlapping at a distance, forming our pi bond. And then we also have, our sp2 orbitals forming a sigma bond. And here's our sp2s orbitals forming another sigma bond, and on and on and on. So the only difference here that we're seeing is we're seeing the molecular orbitals sort of being formed. So as opposed to over here where the atomic orbitals are all sort of separate, here they have formed molecular orbitals. So we say that sp2 hybridization results in a trigonal planar molecular geometry, right? And we can see that here if we look about carbon here, we have 1, 2, 3 orbitals, all dispersed symmetrically, evenly about that carbon atom, and there are no lone pairs there to consider. Remember, then we're looking at the arrangement, not the molecular geometry, right? And here we have 3 pairs of electrons all around our carbon. So we see a trigonal planar orientation. So I'm curious to see if you can make sense, if you can guess what's going on in a molecule of ethine. In this case, we see carbon-carbon in a triple bond. Let's see if we can make sense of that. So maybe pause the video, see if you can work out what the hybrid orbitals might be in a molecule such as this. All right, well, I'm going to go through with the explanation here. I'm going to start as we have before, just outlining the following distribution of electrons into each of carbon's orbitals. And so in this case, I'm going to remind you that, a sigma bond is a direct overlap. And so one of the bonds in this molecule has to be a sigma, in the triple bond that is, has to be a sigma bond. So I'm going to just delineate that. And so, if I'm looking at the p orbitals, I can only have one set of directly overlapping, right, orbitals. Now I also have the other px and py orbitals here as well. Those can't overlap directly, and so that has to be a pi bond. So I'm going to just indicate that here as a pi bond. And so that's formed by one set of p orbitals, so p and p. But I also have to remember there is the third orientation available for p orbitals here, and they can't form a sigma bond either. So that's sort of an at a distance overlap. And so here we are here. I'm going to delineate those as such with a p and a p as well with another pi bond. So in that triple bond, we have a sigma and two pi bonds. So let's look at what we have left over to form hybrid orbitals, right? And so you'll remember that, this bond here on carbon and this bond here, these two bonds, we want to see if we can make them equal length. So we're going to hybridize our orbitals. So what's left? Well, I'm putting in two orbitals. I need to get two orbitals out. So I'm going to just take that and move it down here. So 1, 2 orbitals. So I'm going to get a mishmash of s orbital and p orbitals. But in this case, I have one part s and one part p. So the hybrid orbitals I'm forming are sp and sp. So I'm going to put that around my carbon here. Sp and then sp. I can see I would have to do the same thing, mirroring that on the other side. Right? So that, I hope you did okay with that. And if not, please come and see me for some extra help. And so by doing that, I have these two atomic orbitals around carbon that are of equal size and shape. Now finally, I want to indicate that there's an s orbital on each of my hydrogen, and that I have a sigma bond between carbon and hydrogen on either side of this molecule. So as we did before, I want to visualize this. My drawings can only go so far. So if we look at this, I've got my my py and my px orbitals that can't overlap directly. The geometry just doesn't work that way, and so they're forming two pi bonds. There's one pi between our px's and another pi between our py's. So there we go. But there's also a direct overlap, right? The third bond in that triple bond is going to be a sigma bond. So here we see the sigma bond overlapping of the sp and the sp orbital forming a molecular orbital. And then here we see the sp overlapping with the s in hydrogen. So now let's put this all together. I'm just going to flip to the next slide so there we can see this. So putting it all together, we have, and again, just here on the left, we can see our atomic orbitals before they combine to form molecular orbitals. We can see our px and our py, and then we see our sigma bond here, and then our pi bonds here. And then we put it together, and they kind of mush together to form molecular orbitals. Here is our sp-sp overlap, and here are our pp overlaps. So now we say that sp hybridization results in a linear electron arrangement around the atom in question. So let's visit that. I'm going to redraw our molecule right here so we can see it. And clearly, very clearly, we see that there are no lone pairs on either carbon atom. We see that that would allow us to predict a bond angle of 180 degrees, which is what we would expect with a linear molecule. Here is a practice example for you to try, and in a second here I'm going to go through with it and show you how the solution to the problem. So if you want to pause the video, give it a try, and then come back, then that would be great. Okay, so I'm going to take up this question, and when I go through a problem like this, I like to think about each carbon at a time. So in this case, I'm going to just enlarge this a little bit so it's not as messy. And I usually start by naming all the bonds as either sigma or pi. And so any sigma bond that I have any single bond is going to be a sigma bond. So sigma, 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 and so on and so forth. Sigma, here I have a pi and a sigma, another sigma here, a pi, and another, and a sigma, and then another sigma over here, right? So, oops, I forgot these two, sigma, sigma. So that's one layer to consider. Now, once I know that, I can sort of think about how the hybridization is going to happen. So I'm going to focus first on this carbon right here, and I can see that it has 1, 2, 3, 4 bonds in it, and I can also see that it has a tetrahedral configuration. So that's a pretty good hint that I need to have 4 orbitals of equal size, and the way that that happens is that I create the sp3 hybrid orbitals all around this particular carbon, sp3, sp3, right? So I'm done with that carbon. I need to move on to my other carbon. I'm going to do that next. So, but I'm going to focus in first on this double bond. Now you'll remember that every double bond is formed of 1 sigma and 1 pi bond, and the pi bond is an overlap of a p and a p orbital, which leaves sp2 hybrid orbitals remaining. sp2, sp2. So then, every time I have sp2 hybrid orbitals forming, that creates that trigonal planar configuration, which I can see in this diagram, sp2. So then I'm going to see that mirrored on the other side with the adjacent carbon, right? I have one of my p orbital electrons is occupied. That leaves 2 other p electrons and 1 s, forming sp2 hybrid orbitals. So I'm going to carry on and just depict that in my diagram. sp2, sp2, and there you go. All right, moving on to, I would say, the 4th carbon in my line, in my parent chain here. I'm going to go ahead and identify each of the pi bonds as being formed by p overlap. p overlap. Then, so for each carbon, this carbon here, 2 of my p electrons are in pi bonds, and so that leaves 1 p and 1 s orbital that have to hybridize, and so that will form an sp hybrid orbital. 2 sp orbitals. Remember that if I have an s and a p, I'm beginning with 2 orbitals, so that means my new orbitals, there have to be 2 of them, and they're both just 1 part s and 1 part p. So there I go. And I'm going to see that mirrored on the other side with my final carbon having 2 sp hybrid orbitals. And again, we can see that with that linear configuration, the bond angle of 180 between the carbon and the hydrogen that are coming off of that carbon in question. Hopefully you did okay with that. And if you have any questions, be sure to come and see me.